All right. Am I recording? I think I am. Okay. So let's share again. Great. Okay. So we're talking. Okay. We're talking about graph neural networks. So geometric deep learning was initiated, really the way I'm teaching you now, by Bronsted in 2016. And he thought about it as working on 3D images. So for him, meshes in 3D image, that was his motivation. Later on, we discovered that this method of applying the deep learning algorithm to graphs was useful also for non-3D images, but also for other type of data, okay? But he developed it for that. Then the example I was giving you is very different from like a 3D data, is the example of a social network. That's very easy to understand, right? You have a graph, every person, every user is a node, and then friendship or other is the edges. Okay, so this we discussed. Okay, now we go to the supervised classification problem for graph neural network. So GNN means graph neural network. So we can have different types of classification problems. We can have many graphs. So for example, we have molecules corresponding to proteins, and then we have a label. This protein may or may not be an enzyme. And then we say 0 and 1, and we try to label. So I teach, you know, like with images, cats and dogs, right? I show many, many images of cats and dogs, and then the algorithm after the training can tell us whether or not a given image is a cat or a dog. Same thing, instead of showing images, you are showing graphs that are encoded in a suitable way. Some molecules are enzymes, some are not, and in the end, you show a molecule, it tells you enzyme or not enzyme. And this works very effectively on molecules. And there is a vast area. For example, Welling, Max Welling is working for Microsoft, is doing chemistry with these molecules, the graph neural network. So it is very effective. Or we can consider a different type of analysis, where you have just one graph. For example, Facebook is one unique graph, right? We are all connected in the same, and we want to classify the nodes. For example, nodes have a label. For example, I am a celebrity or not, 0, 1. And then I look at the graph, I learn from this graph, and I try to predict whether a node without a label is a celebrity or not. This is, of course, a different type of problem. In one case, first problem, you have many graphs and you try to classify. This is very similar to deep learning. So you are replacing data, an image with a graph. In the second case, is substantially different because you have just a one graph and you try to understand the label of the nodes. You know many nodes, but you also don't know the labels of some other nodes, and you want to understand that. I tell you, so this, of course, is not giving you all the possibilities, because there are many more possibilities. And in fact, that made my reading of graph neural network very difficult. For example, here I don't treat it, but I'm telling you there is also the example where you are adding a node. Then you understand this is more complicated classification, because this node is added. You don't know the topology of the graph to start with, and then the topology gets modified. You can do that also. Or another thing that you can do, which is even scarier, you can predict whether or not there is an edge between two nodes. You suppose you don't know all the edges, and you can try to predict. I look at two nodes, predict an edge. Okay, so these things I'm not treating because they are complicated. We will focus only on the example of one graph and node classification. Okay, so that's the easy case we are looking, because I prefer to do this instead of going to the more complicated one. if you read the paper of Bronstein, he's very difficult to read because he's trying to advertise. He says, oh, we can do this, we can do that. Yeah, you can do a lot, but how do you do it? So you are kind of getting very confused. While here I prefer to focus on one problem, hopefully. Is it clear what we're doing? Any questions also from the audience? Okay, so okay, so the question that we want to tackle is this very, what can I say, illustrative picture, is that we have a graph, so we know the graph. The graph is given to us. We know the labels of some nodes. We try to predict all the labels. So in this picture, one say, okay, this is a picture very general. No, this picture shows you a strange phenomenon that happens in geometric deep learning. Notice that here we have only 4 labels, the green and the red. And now we predict the labels of more nodes, which is kind of the opposite that happens for deep learning. For deep learning, you know the labels of many, many images, thousands, right? In the Schiffer data sets, there are 60,000 images, and that you know the label. And then you try to predict the test, which are a few thousand. So in deep learning, you have a huge database that is labeled, and you try to predict based on that. In geometric deep learning, you have the graph, which is a lot of information because we know the link between the nodes, but you can perform successfully classification even if you know only few nodes. See here, you know 4 nodes out of what? 9. And still you can predict in this picture. In the Zachary Karate Club that we're going to study, you have 34 nodes. You know the labels of 4 nodes and you predict the others. Very surprising. Why is this Zachary so famous? We're going to go over it in just a moment. It is famous because it's the topology of the graph that is giving you the information. And this is difficult to appreciate at first because when we look at the images, there is no topology. That's a grid, pixels, all ordered. But in graphs, the fact that there is a link or there isn't, it's a strong information. It's a topological information. And that is why what allows you to classify, even if you know very few labels and if you have very few data. And this is why I personally became very interested in geometric deep learning, because if you have a medical, biological database, the links are coming to you for free. And then because there are links, for example, imagine Facebook is friendship, right? But it could be that you share, if you are in a medical database, an illness with somebody. You share a gene, a defective gene. This is the link that can be between individuals in medicine, okay? So this database arrives already. And then the other thing that for biological databases is that there are few, very few data. You don't have thousands of patients. If you're lucky, you have few hundreds. So this is why it is more promising. Okay. So last time I was giving you the perspective on graph neural network. So we concentrate only on the score function. So the loss function and the optimizer stay the same. Then we have to understand the score. The score is separated in 2 parts, the encoding and the decoding. I will try to explain what they are presently. So we have our graph, okay? We forget about the loss function and the optimizer because that's really same as deep learning, forget it. Score, what does the score does? The score gives to each node a score. Remember, there was like image was a cat, and then the score is some number is a dog, some number is a cat, some number is a horse. Same thing. You have your node, the score tells you whether or not it is among a certain class, okay? 0, 1, 2, 3, perhaps, okay? That's the problem. The score gives you this. It is separated in two portions, which as mathematics, as mathematicians, we like. There is the encoding and the decoding. Encoding produces a low-dimensional embedding of the graph. So what happens is that you take your graph and you project it in some low-dimensional space. For example, the plane. So, you know, a graph is maybe a very complicated object, and then you project it. And then there is the decoding, where typically we have a linear layer. You remember linear classification through hyperplanes separates the classes. So the purpose of the encoding is to realize the embedding of the graph in such a way that the different classes are linearly separable. Because once you realize this encoding, you use the hyperplanes to separate the different classes. Do we understand the purpose of encoding and decoding? You don't look like somebody that understands. Go. So two parts. And in principle, there is no reason why the encoding works. And in fact, it may not work, but I'm saying that's a strategy to project it. And I should say, encoding and decoding is learned. So there are ways in which you learn that, as in deep learning. So there will be some matrices and so on. Okay, so we go to the encoding. Okay. So you have a node. Now, this node will have features. Okay, what are the features of the node? So the node has a label that tells you the class, but also have features. For example, for the patients, for example, the label could be I am diabetic or I'm not diabetic. That could be the label of a patient. But the patient comes also with features. For example, my height, my weight, my age. So there are numbers associated to each node. In the example, are you guys with me? I heard the kind of a bad noise. Okay, let's hope you are with me. You are online. I will check. Yeah. Oh, you are. Okay. In the example of the Zachary Karate Club, we will see that there is no feature. Okay, this is also a possibility that there is no feature. So the classification is decided only on the topology of the graph, the nodes I am connected with. I insist on this point because it may be difficult to understand at first that a node has links to other nodes, has a label describing the node, diabetic, not diabetic, but also has features, numbers associated to it. So there are these three things associated to a node. Is different from images, of course, because this is a graph neural network. Other thing I want to say before I leave this slide, the number D can be really small, could be 2 or 3. So you want really a low dimensional embedding, going really very low. Okay. Questions? Now we're going to see how encoder and decoder are actually realized. And I already know you will not like it because it's very complicated, but I will explain. Okay. So I prefer to explain it with the study of the Zachary Karate Club. In this particular data set, there are 34 members of the Karate Club. Okay. And so, fine, 34 people. There are links between people. And these links were established by this guy, Zachary, who, so Zachary Karate Club is not the Karate Club of Zachary. No. It is the researcher who analyzed this little society that, so 34 members, and these are linked with, so each member, you can see the graph. Okay. You can see the graph right here. Perhaps I should make it a little larger. Whoops, sorry about that. No, I can't make it larger. Okay, so I want to show, all right. So I want to show you the graph of the Zachary. Can you see it? Shall I make it a little larger, perhaps? You can see it, okay. So the different colors of the different nodes corresponds to their label. So there is label 0, 1, 2, 3, and the colors are purple, red, blue, and green. And then there are links, meaning that possibly friendship or other things these people share with each other. I don't know. I confess I did not read the Karate Club. And then you see here that we did a very good job with the project on this side. We did a very good job in the encoding. Why is it a good job? Question for the audience. Why is it a good job? She says, oh, I don't know. She says it's a good job. Why is it a good job? Exactly. Perfect. That's a perfect answer. Because with this embedding, you see that we project this complicated graph into two-dimensional, and it is linearly separable, almost. Not fully, but almost linearly. That's the idea. This is, of course, I mean, this is a very simple data set. We don't need geometric deep learning to do it. But I'm just telling that this is an example on how this is working, okay? So certainly people will not use geometric deep learning to solve this problem. This is a very stupid problem, but hopefully you understand. Now, there are no features for each node, so we take every, what can I say? We think of a node as a vector in 34 coordinates with 1 in one position. So it's like the canonical basis of R34, right? 1, 0, 0, 0, 1, 0, 0, and so on. There are no features. That's the way it is encoded to start with. And the encoding function sends this R34 into R2, okay? But how do we obtain? So you understand, there is no chalk. I wanted to write R34, 32, but I cannot. No, Maurizio, I don't want you to go. Perhaps you also need it later, perhaps. Yeah. So we go from R34 to R2. How do we do this? For the images, the equivalent are the convolutions. Okay, so there is the encoder that gives me the function f from R34 to R2, and there is the decoder that is a linear. So we go from a space of 34 dimensions to R4, then we do R4 to R4, then R4 to R2, and then R2 to R4. Why do we go to R4? Because the score is 4. 0, 1, 2, 3. So we need in the end to output 4 numbers. And we do it with the convolutional on graph, the convolutions on graphs. Grazie. Okay, so now I show how to do the convolutions on graphs. Is it clear the structure, the logic? So we do encoder, we do decoder. Decoder is simple because it just tells us how to separate the linearly separable points in the plane. Okay, that is... Okay, so for this part, I'm looking at Leskovec course. Okay. Perhaps since I want to leave the floor to Maurizio, I will go kind of fast. This is saying something kind of obvious that if, so you want a link occurring to nodes that have common similar features and labels. Because if you are connecting things that don't have anything to do with each other, clearly you don't obtain a meaningful classification. Okay, so that's, I know it's kind of obvious, but it's very important. Okay. So here I'm trying to explain what is the problem with convolution. And I think that you already realize what is the problem, because you see here on the green, you see images and text. This is where deep learning is very, very effective, right? You remember the convolution sliding across images, sliding across, you can think about sliding across vectors. So this is how natural language processing is done. It's very successful. Now, if you try to do convolution on graphs, you encounter immediately a huge problem, because it is clear that what can you slide? There is not a little 3x3 matrix that you can slide, because the graph is different at each node, potentially, right? So you don't know how to do this. How do you solve this problem? So you solve it in the possibly simplest way. Okay, so I'm saying it is not possible to perform convolution using filters as in the image. Okay, how do you do this? You do with the mechanism of message passing. Okay, so let me show you this slide, which perhaps it is clear, perhaps it is not. We are mathematicians. So these are the slides of Leskovec that is talking to computer science people. They need to see pictures so they feel more reassured. I personally am not helped by this picture, because what does a picture mean? I like the formulas. But nevertheless, I propose this picture because the idea is the following. If you're doing a convolution from the, so let me try, I will definitely show you the formula in a moment. So you have a node. You want the node to get the information of the nearby nodes. So you remember with the image, you had the pixel, with the filter was getting the information of the pixel all around. Same thing. So the node A must get the convolution information by the node B, C, D. Okay? Now, the point is that if you're doing the same thing to B, C, D, you're getting, so same thing, B gets the information from A and C. C gets the information from A, B, E, F. You see the point, right? And then if you do it more than once, it's like the first time A gets information only of the one around it. But then since you're doing it for every node, the second time around it gets information also of a larger neighborhood. Okay, that's the idea. That's the concept of message passing. First time you do it only around, the second time, because you did it for all nodes, you get it the second neighborhood. And depends on you. How much do you want to go? You can stop after one neighborhood around, or you could repeat this twice and get the second, or repeat it 3 times, as you want, okay? What people do? People do it 3 times. Why? Because they do like that. There is a reason why you don't want to do it many times, because if your graph is not very big, if you do it too many times, you're sort of mixing everything together, so you're not obtaining information. Because like the filters, you want an information of what is near it. You don't want information of something that is very, very far, right? So if you keep doing it, you get the whole graph into it. That's not good. You do it once, twice, perhaps 3 times, that's it. I'm going to show. So this is the idea, okay? Now we show how it is done. I am sorry, I should have turned off my, no one ever either calls me or send me messages, so probably my children, they want money. No, but no one ever calls me or send me messages, so I feel very safe. Okay, here is the formula. For the sake of clarity, let's ignore B for the moment, okay? Let's assume this B is not here. So let's try to give an explanation. H is the feature. Perhaps it is a vector, perhaps it is a number. No, vabbè, adesso basta. All right, done. So in the zero step, which is this box, H0 is giving you the feature X. That's a feature you are assigned. Perhaps the feature is my height. Okay, that number. Okay. Then at the step 1, because K is 0, right? So K plus 1 is the first step when K is 0, great. What do you have? Focus on this blue thing. You're looking at the vertices that are in a neighborhood of V. So that N means neighborhood, okay? So you have, so this is your V, and there'll be some U1, U2. So these are the U3. So the neighborhood of V is U1, U2, U3, okay? So you look at the set of all the vertices that are connected to V. And look what you do. You are taking all the features, so these are HU, and you divide by how many. So you are distributing the information divided. So you are getting here the feature of HU1 divided by 3, HU2 divided by 3, HU3 divided by 3. So you are summing all this contribution divided by the number. So they're not doing something very smart. This, we could have come up with it, because it's like you are having the features on the neighboring vertices and they contribute as a fraction. They're equally distributed, the information. Now here you put the matrix of weights, okay? Usually H is a vector, so it is a matrix. If H is a scalar, there'll be a number, okay? We understand? And then there is a non-linearity, the ReLU, for example, but that is a minor point. The non-linearity is same as in deep learning. Do you understand the message passing? Somebody is... yes, Margarita, this is correct. This is what people call also the aggregation of neighbors' features. Yes, I didn't use the word aggregation because for me it's just a word. I wanted to pass the concept. So this is the message passing. Okay. Yes, she's, and then people say aggregation, concatenation, but it's like, okay. Do we understand? Get information of the neighborhood, and then you repeat a certain number of times. So this is one layer, so you do it once, it is one layer, and then you do it twice, and you get a second layer. And in, yes. No, so
HU1 is different from HU2?
Of course, because for example, I am this node, my height is some height, you are this node, your height is a different height. No. The message, the message goes from the neighboring. So the new value of HV, which is here, the new value is the aggregation. So you sum the contributes of the nearby. Okay. You could stop here if you want. So you get a new value. This value will be the average of the, but notice that you have a B here. Okay. So the B, when B is non-zero, you get the average of this plus the original value because there is B summing.
And WK is a
WK, if H is a number, like the height, WK is also a number because it multiplies. If is a weight, if, for example, we associate my height, my weight, my age, then it will be a vector, then W is a matrix. It depends on what it is your feature. Usually it is a matrix, okay? The typical thing is a matrix, okay? You do it for 2 times, 3 times, and you get because the first time you are aggregating this. But remember, you are doing this for all nodes, right? Which means that the first time you aggregate what is in U1, what is in V, what is in U2. The second time in V arrives the information also of the others, okay? So that is the message passing mechanism. Very plain, very, very plain. Any questions on this message passing? Sort of. Okay. Now this is the GNN, graph neural network. Okay. Now the message passing and neighbor aggregation is permutation equivariant. Maurizio will speak to you a lot about equivariance in the next hour, but I think it's worth noticing that in this operation, it shouldn't matter whether you aggregate, see the order in which you aggregate, because that's a summation. So it doesn't matter if you exchange U1 with U2. That obviously is no. And this is a very important fact in graph neural networks. There are some natural invariants for some groups. And this can be studied mathematically. They have an interesting, what can I say? It's an interesting area, and Maurizio is a very expert, way more than me, so he will say later. Absolutely, yes. Yes. Yes, yes, to start with, yes. No, I understand you. Let me try to see if I understand your question. So you have this mechanism, right? At the beginning, the weights are random. So at the beginning, all this procedure gets inside the feature, gives you back some features which are very changed. They're changing dimension, they're changing value. And then there is a linear layer in the end that outputs a scores, okay? Which are certainly wrong because we start. Now, these scores go inside the loss function and the optimizer. And then based on the loss, they say, oh, wait a moment, it is really bad. So we do the gradient descent and we go towards a minimum of the loss. We know it's not really a minimum, but we go down. And then we start again with a new, okay? So this is one run, and we know there are many, many runs because first of all, we do like lots of epochs, right? I will show you. Here less epochs than deep learning. Yes. Exactly. So it's a very good point. So the information about the topology comes exactly in the message passing right here, because we are saying which ones are the neighborhood. And these are the only ones that contribute towards the change of features in one node. So something that is far does not contribute, something that is close will contribute. Okay, so this is, no, but thank you. So any questions from the audience online on this very important mechanism? Now, there is a question that you should ask me. Let's see. Because you see that here, we are really averaging here. So the first instinctive question is that, well, we are learning all of this. See that W, this weight matrix, is outside of the sum, right? So which means that we're doing this process of averaging. So all links are really counting the same. But perhaps there are some links that are more important than others, right? And this is not the message passing, because in message passing with the aggregation, there is no way. It is the next, is the graph attention that is able to do this, okay? So here, all the links have the same importance. In the next mechanism I show you, is not like this. But let's finish the example of the Zachary club. Okay, so in the Zachary Karate Club, we play this convolution. So we go from the feature H0 to the feature H1. Then we do from H1 to H2. The dimension changes until we reach the last one after 3 layers, that is dimension 2. And then we separate. I think I have a picture, but I may not have it. I don't know. Do I have a picture? No. I decided to. I'm sorry. I had a very nice picture, but I put it in the notes, not in the slides. Too bad. So I just want to give you the metric. We have for training just 4 notes. Very few 4 notes. 1 for each class. 1 label 0, 1 label 1, 1 label 2, 1 label 3. Amazing, right? It's like showing 1 picture of a cat, 1 picture of a dog, 1 picture of a horse, and that's only one, right? And then we use as test as 30 notes. And the accuracy is 71%, which is just amazing. That is, of course, this is a toy example. Shouldn't draw conclusions, but it's very good. Any questions on the Zachary Karate Club? Do we understand this message passing? Now, the next case study is the core dataset, and it is graph attention. So very briefly, because I want to leave the floor to Maurizio, we want to be able to specify the importance of single links. And for this reason, we do what is called the attention strategy. Morally, what happens? I perhaps skip the theoretical treatment. We want to, so if I have a vertex B and another vertex U1, I want to associate a number to this link, period. I associate a number. And this number will tell me the importance. So the number is between 0 and 1. 0, the link disappears. 1, the link is very strong. And we learn this through weights. So, right. Sorry, I was supposed to. So I show you. See, this is how these alpha ij are the coefficient that are assigned to a vertex between vertex I and vertex j. The link is undirected graph, so there are no errors, it's just that. And as you can see, it is a number between 0 and 1. That is, and it is also a number that you see distributes the importance. So the sum of the importance is 1. So this is importance 0.5, 0.3, and 0.2. So it tells me which links around a certain vertex are the most important in the algorithm. So I'm almost finished, Maurizio. So in the attention mechanism, you see the difference. Now, this is a very bad formula I got from Leskovec. W does not depend on the vertex, should be outside, right? What is really important is the coefficient. So you get the same formula as before, but with the number alpha inside. Okay. So it's called attention, inspired by cognitive attention. This is one of the things they say. And this is the mechanism. Do we understand what is doing? This assigns a parameter to each link between 2 nodes. This is okay. All right. So I'm also showing to you in this slide the difference, but I think that you guys are very smart and you already figure out it is this alpha. In a message passing, there is no alpha. In graph attention, there is the alpha. The mechanism is similar. And we don't divide by the neighbor because, see, we don't divide by the number of vertices because we are assigning that fraction directly as a coefficient. Okay, so this is okay. Now, any questions of, here I forget the B, any questions about this mechanism? I just want to illustrate the example where it was used, and then I'm finished. Also from, there is a question in chat. Multi-head attention, evidently, Margarita, you are ahead of all of us. And no, we don't do multi-head. This is a very simple mechanism of attention. No, I'm not expert in this at all. Now, okay, I want to show to you the paper by, I think it's Leskovec, I forget, that was using the attention. So it's using the Cora dataset. There are 2,708 scientific papers, and each paper is equipped with features. So the features were either some characteristics, like the word Lee appears, the word, I don't know, variety appears. So these are the features in a paper, and two nodes are connected if the two papers cite each other. So, but it's enough just one of them cites the other. So is an undirected graph, one paper cites the other, there is automatically a link. That's how it is constructed, this data set. And then there are node labels corresponding between, machine learning, mathematics, physics, so they assign. Actually, this algorithm is really used because when you try to post a paper on the web, it will suggest you, say, oh, we think your paper is in this category. So they really use it. So the way they train it with 140 papers. So remember, there are over 2,000 papers, but they train only with 140 nodes. And still, we get an accuracy of 95%. So it is really impressive what these graph neural networks can do. Questions, because I am finished. I'm ready for you, Maurizio. So we take like a 5 minutes break. But before we take the break, are there questions? Okay. All right. So we resume at 4:30, and then Maurizio will speak. Perfect. Okay, so